actually, my start in this business begins with that same Inez Fung paper that I think Dave talked about, or was that Dave Schimmel? So Inez had these beautiful curves of ecosystem net flux, and she drove her global model with it, and they were just gorgeous. And I looked at that and I said, well, nobody has ever measured that anywhere. This is something we should try to do. And so with some considerable help from Dave Fitzgerald, who I think is the next speaker, we kind of mastered the art of doing the eddy covariance. And we had a slightly different approach than what the agricultural people had been doing and those that were in Fife. And we really wanted to do it year-round, unattended, year-round. And that was hard at the time, very challenging. It's much easier now. But we were able to actually do it. Then Boreas came along. We had already started these measurements at Harvard Forest with Dave as a collaborator and had shown that we could do this. And Boreas came around, and Pierce had a really, really beautiful concept for Boreas, Pearson Forest. When I say beautiful, I mean that they had thought the whole thing through, and they knew exactly what they wanted to do. And Pierce discussed, and Forrest, some of the motivation of this, which was largely focused on fluxes that were measured over time scales of hours or days or weeks, things that were could be directly related to the weather stuff that Alan talked about, and that were related to other things that you could model directly. And we were interested in the longer time scales. And so we had some very contentious discussions about whether or not we could do year-round measurements as part of Boreas. Boreas was just beautiful matrix of measurements and modelers and whatever. We really wanted to do it. And eventually they agreed that we could. And so one other person who really played a major role who hasn't been mentioned yet is Diane Wickland. So Diane was the project manager. And the kind of thing we wanted to do, it doesn't really fit in the NASA matrix that well. But because of the powerful arguments made by Pierce et al. And Diane's willingness to really push the envelope on what was going to get funded and what problems we were going to try to solve in the NASA framework, like climate-related problems, we were actually able to do it. And as you'll see, the results turned out to be really, really interesting. So I didn't mean to do that, sorry. So many of you are familiar with the site. I'm not going to spend too much time any time on discussing this, except for that little box there in the red, which is a soil core taken in the moss, in the sphagnum moss domain. And you see this very overly well-drained, aerated stuff at the top. You're not sure where the vegetation starts and the soil stops. And then it goes on down for about 1 meter until you get to highly degraded peat, which is usually either frozen or waterlogged, and that's why it's still there. We're going to come back to that in a minute because that's quite important. This is a picture of the site. It's very heterogeneous. So you look out on the boreal forest, particularly if you have it really flying high. That's not what they did here, but it looks pretty uniform. See little patches, but mostly it looks pretty uniform. You get down on the ground, it's not uniform at all. So these were old black spruce, 120 years old on the right, and then either a boggy fen or a rich bog or something was there. Also well through the area with a lot of deciduous plants there, ericaceous shrubs. Here are the people. Allie Dunn was a graduate student at the time. She's now a professor at Worcester State. Lucy Hutira, also a graduate student, now professor at BU. Carol Barford, who's at University of Wisconsin. Al from Brighton, John Budney, technical people working there. This is a record of temperature and precipitation at the site and surrounding sites. The surrounding sites have data going back to 1970, actually Norway House back to 1900. And what you can see is that even though we're in a global warming scenario, and if you look at just the summertime data for Norway House, you can see a very clear progression of temperature warming from 1900. If you look over a period of a few decades, you don't see it. And that's because, climate is highly variable, and this part of the world has a highly variable climate. And that turns out to be intrinsic to what I'm going to come to in the talk, because it's just extremely important to recognize that these systems, from the top of that core, responds, in minutes, right? The leaves on the trees responds to environmental forcing in minutes. The bottom of the core, which is only a meter away, is centuries. And in between, everything else that you want. And some of the parts of the ecosystem are responding at multiple timescales, just that one part. So the tree structure, all that stuff. And so if you really want to understand how climate is going to affect the carbon stores and what kind of feedback you're going to have in the climate carbon system, boreal in particular, you're going to have to be there for a long time. And you're going to have to, since you can't be there forever and you can't go back in time, one of the things that we were trying to do in Boreas, which met with some success, and not complete success surely, is to be able to use this wonderful framework that was built up as part of Boreas to really understand what we're seeing and then be able to introduce it into models. And there I think we both had a wonderful success in the sense that we really did understand what was driving some of this on the ecosystem scale, and a complete failure in the sense that the global scale models do not include any of these as far as I can tell. So we're going to get to that in a minute. This is a soil temperature record at 20 centimeters and 50 centimeters. The first thing you notice about this is that the summer and the winter don't necessarily co-vary. The cold periods and warm periods, the anomalies are not necessarily that well correlated. Another thing you may notice is that there's some flat periods in there, which we're going to talk about in a minute, where the temperature seems to be thermostated, because it is. Just another indication of the type of variability that you have here. This is the length of the growing season during the period that we're there. Oh, you notice we didn't stop at the end. This is another tremendous tribute to Diane Wickland and also Hank Margolis, who's here in the audience, because after Boreas, we got funds to continue. After NASA said, okay, this is just too much of a long-term study, we can't do it, Brian Amiro took it over until he ran it for almost no money. But you can't run it for no money. And when it came to no money, you can tell there was an election in 2006 in Canada, and that was the end of this thing. So it ends in 2006. But during that time period, you see a lot of variability. This is the length of the growing season, critical parameter. You don't see a trend, even though climate is warming in a very steady fashion. Okay, this is the slide I'm going to spend most of my time talking about. Not most of my time, but want to really focus on this slide. On the left side, you see the eddy flux net data. This is like in 2 months, 2 week averages over that entire 12-year period from 94 to 2006 of the data. And what you can see is that in the springtime and early summer, there's net uptake, then it seems to die, and then there's net output that continues actually for quite a while. So on the right is just the net term blown up in a bar chart. And you can see quite an extraordinary amount of output. After the first round of Boreas, everybody had packed up before that. So once we showed the first year to Forrest and Pierce, they said everybody will be there in 96 for the whole year. And I think that actually worked out pretty well. What you actually see if you look carefully on the left side, the green curve is the uptake and the black curve is the respiration. And you can see that they have pretty similar shapes and pretty similar magnitude. The green curve is phase shifted to the left. And it has an asymmetry. It starts up a little more slowly than the respiration. The respiration kind of picks up quickly. The green curve picks up more slowly. And that both the phase shift and that asymmetry gives you the uptake at the beginning. At the end, it's reversed, right? The green curve has been shape-shifted to the left, so the uptake is dying out more quickly. And the respiration has this kind of tail at the end. And we're going to see why that is. And then we're going to see why we're so disappointed that this knowledge, which has been out there now since this work in Boreas, hasn't made it into the global models. Okay, so I'll see if there's anything else I wish to say about that. I don't think so. You notice it continues through the winter. So it's an area of discontinuous permafrost. And most years, even at 50 centimeters, the soils never freeze. You get enough snow on there to insulate them, and they're not frozen. But they are frozen at the top, and we'll see why that's important in a minute. Okay, this is a set of temperature data. The gray curves are at 35 centimeters, and the black ones are at 15 centimeters, and in different places. So there's tremendously important topography in here, as some other speakers mentioned. It controls everything in terms of the variability that you see. The extent of the topography is only a few meters. So it's not like Fife with this kind of rolling stuff. But the fact that you have low spots and high spots matters a lot. And so that's showing some difference here. You notice this very long period in the springtime when the temperature is thermostated in the soils. And we'll see why that is in a minute. In the fall, you also see that, and that's actually for a different physical reason, as we'll see. Okay, so we installed a well. And you say, well, we're going to try to do a well. We're in the boreal forest. How do you make a well that records all year round? So we put a little sonic rangefinder and a plastic tube, a piece of sewer pipe, and it all was good. And so we could record the height of the water table every 5 seconds. And we found some really interesting things. There's a very large diurnal variation in that height, which represents basically pore pressure in the soil. There's a whole other story. But what you see is that at the beginning of the year, in the springtime, the water table is way up high. It's near the surface. It hits 10 centimeters sometime in early to second week of June. And then it finally melts out almost at the beginning of July, just a few days toward the end of June. And then when it melts out, the water table crashes. So what's happening is that you have frozen soil here. You have about 30-some centimeters of rain per year. So this is a desert, but it's not that much of a desert. And it has plenty of water in the springtime to saturate the surface, upper part of the soil. So you have an ice lens, and we have all this in the temperatures as well. You have an ice lens, and on top of the ice lens, you have a perched water table. Underneath the water table, underneath that perched water table, it's not saturated. And that perched water table is suppressing the respiration. And that's one of the key things that's driving the respiration curve to be later, and that gives you that spring pulse of uptake. So it's actually not rocket science to imagine modeling this, right? Joe showed some of the equations that went into the global models. These are simpler if you really wanted to, there's some parameters to deal with, but it's not that hard. And then later on, when it actually freezes, there's nothing funny going on with the water table. And so let's go back. Let's look at another example of that. This is a different site now, it's a wetter site. Now you can see that really, really long time when the water table is basically ice water. It's right at the ice temperature, but it's water. And then on the other side, you have this long flat period, and that's called a zero curtain. And what's happening there is it's not saturated with water, but you're trying to freeze the soil. And the soil fluids, it's not pure water. And still there's some latent heat to be removed, but there's snow on top. The heat fluxes are very small. It takes a long time to get the heat out of the soil. In fact, it takes all winter. There's still heat trapped in the soil. So what's happening there is that during that time period, it's a big surprise, the bacteria are very, is that me? No. No, okay. The bacteria are very active. It's a huge surprise if they're supposed to go to sleep at zero. And it wasn't until 1969, was it? What's his name? Coyne and Kelly wrote a paper in which they saw this in the tundra, and they took a core in the summertime and froze it and showed that the bacteria were active. So it was only known for 30 years or so before this, and now however much time additional has passed. And as far as I can tell, none of the global models have a zero curtain.
Zero.
Has a zero curtain, meaning a time period when these types of soils are poised at the 0 degrees and respiration is going like a banshee. It's just rolling. And that's really what's happening here. So this has been known. It's all published in that paper that I showed on the beginning slide there, the Dunn paper in 2007. We didn't discover it. It was known really back in time, although the Boreas framework and these year-round eddy flux measurements combined with the biophysical measurements allowed us to really do a much better job in characterizing it than people had before. And I think provide the basis for potentially including it in global models. Okay, so what happened there? That is not good. What happened here?
Got the help window.
I got the help window? What did I do?
Your screen is good.
That's fine. Okay. I don't know what I did. I think it'll be better if I use this little button here. Oh, I'm going backwards. That's even better. Sorry about that. Okay, so I can now take, now I want to show the surprises. So when we did Boreas, we had it ran from 94 to 97, and the Oldbrack spruce site on average was a significant source of carbon to the atmosphere for this region. You know, it's about a ton or between half a ton and a ton of carbon per hectare per year. That's pretty big for this type of environment. And so had we stopped then, that's what we would have thought was the case. Then it leveled out. So, whoa, big surprise, it levels out. And then it turns around and goes the other way and starts to become a sink. And there are lots of excuses we can make for that. Oh, maybe the ericaceous shrubs are coming in, there's more deciduous tree plants, and da-da-da. There are a lot of excuses we could make. But in this case, because we still had a lot of the Boreas framework, we knew what was actually happening. So we can go and say, oh, interrogate it. What's happening? Well, first thing you can do is you can say what time periods are contributing. The green curve is the middle of summer. And you can see that yeah, it has some trend, but it doesn't actually explain that trend. What does explain that trend is what's happening in August and September. And in August and September, the respiration rates are going down. So, so you're basically switching from neutral to a weak sink, and that's basically a lot of what's driving that thing. Why are they doing that? Well, so Allison made a bunch of regressions. We had zillions of things to regress against. It turned out that that two parameters could explain something like 80% of the variation that you saw over those 10 years of data. She had only 10. There were two more that Brian took that she didn't analyze. But they're interesting to see what they were. So one was a precipitation index for the previous 3 years, not this year, the previous 3 years. And or you could take the previous 2 years, almost as good, previous 4 years. But basically, it's an integrated measure of the recent history of precipitation that tells you something about where the water table actually is. It tells you actually a lot of things, a lot of biophysical things. And the other predictor was this year's PET, which is temperature, right? But it's this year's, not the previous years. And those two predictors account for something like 70 to 80% or 90% of the variance. And so what that tells you is that there isn't any evidence. Now there may be some change in vegetation, but there isn't any evidence that a change in vegetation is causing this. This is just a response to climate. These systems are very slow. They remember what happened years ago, and that's basically the story. Okay, so I have just a minute. How much? I lost a minute, right? Can I take just a couple minutes? Okay. So, so how did we change our views about what we do? So one thing was when we did this CARVE experiment, which was an EVS1, Carbon in the Arctic Reservoirs Vulnerability Experiment, I can't hardly get it out. We had 3 years of aircraft data, and we had some ground data and all this type of stuff. And this is not an eddy flux measurement, but it's low-flying airplane that jumps up and down, and we do inverse modeling on the on the measurements, and we don't want to go there, but you can see the flight tracks are kind of all over northern Alaska over a 3-year period. And we see these vertical profiles. The one on the left is at the beginning of the growing season. You can see a bit of a drawdown. We have a really, really good prior, something I could talk to Alan about, because we have a really excellent prior that's remote sensing driven. And we can then assess what the fluxes are over time. And this shows what we get. So the red points are the 3 years worth of monthly net ecosystem exchange for that northern area. And we can divide it by ecotype if you want. And what you can see is it looks a lot like the Boreas does, right? There's a big fall output. The uptake kind of peaks sort of early in the summer, a little later actually here than there, as you might expect. And the green curve on the bottom is the very best of the models that was used in the IPCC. None of the others are even close. So there's like 12 models. The others are all nothing like what not even close. But this model is sort of not too bad. The phase is off for a variety of reasons that we don't really fully understand. But then if I look at those upper two figures, the one on the left is plotting the seasonal amplitude of the CO2 uptake. And the one on the y-axis is the growing season net uptake. And you can kind of see there's some relationship between those, as you might expect. And our point is the red point, so there's like 1 point that comes sort of close to that. The one on the right is even more interesting. The x-axis is the early winter respiration. And the y-axis is the total net annual ecosystem exchange. And you can see that only a few of them come even close to getting anything like the early winter output that we see, because they don't have the mechanisms that we just talked about. And almost none of them, those that get actually a net source for the region, which is what we're seeing over the 3 years, are not getting it for the right reason. Okay, so I'm sorry I don't have time to talk about the 40-year trend experiment that we did by looking at the Barrow data, and I'll just wrap up right here. So here's how Boreas changed the way, at least I think, we think about seasonal cycles and long-term trends. You really need to mind the shoulder seasons if you're going to do anything here. The second thing is that the combination of remote sensing, aircraft, and ground-based observations is the only way you're going to get at this stuff. And you can do short-term, long-term, they need to be blended together in a proper way. And hats off to Pierce and Forrest and Diane for making that happen. And the last thing is, if you want to understand the soil-climate nexus, you might think about modeling the soils in the global models. And they have stuff under there, but it's just not very good. And so we're going to leave it at that. Thank you.
Okay, thank you.